In this video, we're going to go over all the characteristics of the parent function y equals 2 to the x. So y equals 2 to the x, I'm going to start with the graph. Y equals 2 to the x has a horizontal asymptote at y equals 0. And we know that that describes end behavior. And quite honestly, this horizontal asymptote is really applicable only on the left-hand side of our graph. And you'll see after I graph it, or if you're already familiar with this function, you already are visualizing that horizontal asymptote only being applicable when x gets large negatively. So I'm going to start by putting a 3 in to my function for x. And when I put a 3 in, I get 2 cubed, which is 8. When I put a 2 in, 2 squared is 4. When I put a 1 in for x, 2 to the first power is 2. When I put a 0 in for x, 2 to the 0 power is 1. When I put a negative 1 in, 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4. And that value, as I move to the left, is going to, the output is going to get smaller and smaller and smaller. It'll never quite be 0 though, hence the horizontal asymptote. So our domain for this function includes all values from negative infinity to positive infinity. We also call that all real numbers. Therefore, the domain is not limited. The range for this function, all of our outputs, are all positive values. So starting at 0, but not including 0. That's a parenthesis, not including 0. I have an intercept, which is a y-intercept at 0, 1. And we have that horizontal asymptote at y equals 0. This is an increasing function over the entire domain, so over all real numbers, and it is continuous. It is a continuous function. Now, if we reflect this function over the y-axis, that means we put a negative in for x. Y equals 2 to the negative x, where we were putting in a positive 3 and getting 2 to the third. Now I have to put in a negative 3 to get 2 to the third. So we put a negative 3 in, and 2 to the negative 3 would be 8. When we put a negative 2 in, we get 4. When we put a negative 1 in for x, we get 2. When we put a 0 in for x, we get 1. When we put a 1 in for x, we get 1/2, and then 1/4, and so on and so forth. So you can see the graph is going to approach the horizontal asymptote of y equals 0 again, but this time it's going to approach y equals 0 as x gets really, really large positively. So the domain of this function does not change. The domain is negative infinity to positive infinity. The range is still 0 to infinity, not including 0. The intercept is 0, 1. The asymptote is y equals 0. This is an increasing function over all real numbers. I'm sorry, it's decreasing. That is interesting that that says increasing. On my notes, it says decreasing. Hopefully on your notes it says, no, I think on your notes we have to correct it because I'm using your notes, not mine. So decreasing, I apologize for that. That is a decreasing function over the entire domain. So as x gets larger, let's write that. As x increases, y is decreasing. So as x approaches infinity, y is, I'm not going to say approaches negative infinity because it doesn't approach negative infinity, y decreases. So as x increases, y decreases. Yeah, that's a great way to say that right there. This notation right here. As x increases, y decreases, therefore it's decreasing. I'm going to highlight that just to make sure that you've got that. As x increases, y is decreasing. And it is also a continuous function. So we're going to be working with those two parent functions. You can say, really the parent function is y equals 2 to the x, with y equals 2 to the negative x being a reflection which let's talk about that right here, translations and reflections. These are our shifts and our flips. So y equals, if I have a to the x, that would be a base raised to a variable exponent, and that's what makes this an exponential function. If I subtract c inside the function, it would look just like that, and subtracting c inside the function would be a move to the right c units. So we'll just take the entire function and move it to the right. If we have y equals a to the x and we add c inside the function, that would go, that whole function, that graph would move left c. And then we have adding and subtracting outside the function, and what that would look like is a plus c outside of that exponent. That would be a move up. And subtracting c outside of the exponent would be a move down. And then we've got our reflections. So we can have a reflection where we're taking the opposite inside the function. And when we do that, we have that opposite inside would be a reflect over the y-axis, which is what we demonstrated above. And when we have a negative on the outside, that means I'm going to take all of the exponential function a to the x and take the opposite of it. That would be a reflect over the x-axis. And when you have your reflections, that's what's going to determine your increasing and decreasing. So your function will be increasing when x increases, y increases, and it'll be decreasing when x increases and y decreases. So let's just try a couple of problems here. We're going to keep it simple. Y equals 3 raised to the x plus 1 power. My first step is to graph the parent function. Y equals 3 to the x. And I'm going to graph points, but I'm not going to connect them. So when I put a 0 in, I'm going to get a 3 out. I'm sorry. I'm looking at the original function. Okay, so we're going to graph this function right here, y equals 3 to the x. So when I graph y equals 3 to the x, when I put a 0 in, I get a 1 out. When I put a 1 in, I get a 3 out. And when I put a 2 in, I get a 9 out. So the bigger the base, so the bigger this base is, the fewer points that you're going to have to plot on your grid. That's a size -10 to 10, -10 to 10. And then when I put a -1 in, I'm going to get a 1/3 out. So I just put that fractional point right there too. After I graph the y equals 3 to the x, that's when I do my shift. So this shift right here, plus 1, is going to be left 1 unit. So I'm going to move each one of these points. I'm going to move this point, left 1. Move this point, left 1. Move this point, left 1. And move this point, left 1. So what does that do to my horizontal asymptote of y equals 0? It doesn't do anything. So I'll show you. I can, moving it left 1 doesn't affect the asymptote. It's still going to be at y equals 0. So this asymptote will still be at y equals 0. The only time your horizontal asymptote is going to change is when you have an up-down move. So now I can take these points and I can connect them. So I've moved all of the points. I shifted the whole graph left 1. I'm doing my best, and it's all we can hope for, right? There you go. We've got our graph. So what are our intercepts? So we've got our asymptotes that they want to know. We've got our intercepts that they want to know. And we've got to state whether this is an increasing or decreasing function. So this is going to be an increasing function because as x increases, y increases. And our asymptote is y equals 0. And our intercept is 0, 3. Now there's another way to find the intercept, and I'm going to kind of show you right here in this area on the graph. So I've got the x-intercept. Remember, this is always a good thing to know, is that the value of x when y is 0 is the location of your x-intercept. So algebraically, we can always put a 0 in for y and then solve for x. So when will this function ever equal 0? So before we get into logarithms, we can think of this intuitively. And intuitively, this is not possible. Because a base raised to any power will never be 0. So that's not possible. The y-intercept is the value of y when x is 0. So y equals 3 raised to the 0 plus 1, which is 3. So that would be 0, 3. So somewhere along the line, this algebraic process is going to be very, very helpful for you to check your answers, especially if you're taking a test or a quiz and you want to be sure of your answer. So we want to use a couple of tools in our toolkit. Okay, what happens if I have y equals 3 to the x? We'll use 3 as a base again. And we subtract 2 outside of the function. Well, I always go through the same process. I graph the parent function of y equals 3 to the x first. So I put a 0 in and I get a 1 out. I put a 1 in, I get a 3 out. I put a 2 in and I get a 9 out. I put a negative 1 in, I get a 1/3 out. And I know I would not highlight this myself if I were you because you're going to have to erase it. I can move this. See, I can move this, and it's going to have to be moved because of that down move of net -2. So I'm just going to show it there for purposes, but don't highlight it on your paper. Second step is going to be a down shift 2 units. So that subtract 2 on the outside is down 2. So that's going to move our asymptote down 2. So I'm just going to move that right now, 1, 2. So that's why our asymptote is now at y equals -2. I'm going to write it on the other side because it really applies on the other side, and I should have done that earlier. It doesn't matter though. Y equals -2 is our asymptote. So each one of these points is going to be shifted down 2. So rather than, you can't just on your paper take this point and move it down 2. So I'll show you on this problem what I do on paper. I just shift it down 2, down 2, down 2. And then if I'm particularly careful, I go back and I erase each of the points that I just shifted so I don't confuse them. And there's our function. So what's the asymptote? It's y equals -2. The intercept, there's a couple of intercepts here right now. We've got 0, -1, which is very easy to see from the graph. But the other intercept is going to be right here, and it is not a lattice point. So I'm going to come back to that in just a second because I am on a roll. Increasing or decreasing, this is also increasing because as x increases, y increases. So let's talk about that x-intercept. When it's not a lattice point, we have to look at this algebraically. And I believe that you do know enough, I hope, about logarithms to follow me here. So Let's try this. We've got y equals 3 to the x and then minus 2. And I want to find the x-intercept. The x-intercept is the value of x when y is 0. So I have 0 equals 3 to the x minus 2. I'm going to add 2 to both sides. And now the basic definition of logarithms is you can take an equation that has an exponent and you can write it in log form. And that's all we're going to do here. We're just going to write this in log form. This would be log base 3 of 2 equals the exponent of x. So my x-intercept is going to be log base 3 of 2, comma 0. Now, if you need a refresher on that, that's fine. You're going to be exposed to all of that, and I will explain this in more detail in a future lesson.